Welcome to day one of our event. Thank you for joining us this morning. I am Cami Novelli-Kalin, and I'm the Director of Product Management for Amazon Elastic Block Store. And I'm here with John.
Hey, everybody. John Hayden, Director of Engineering for EBS.
So today, we're going to take you on a bit of a journey behind the scenes of how we've built Elastic Block Store. This year, we're celebrating 15 years since we launched, and we're going to tell you a little bit about how we've scaled and how we've kept up with what you, our customers, needed from us over the years. And so we are going to cover a little bit of the history of EBS, but in reality, this session can really be about any large-scale distributed system built in the cloud and how it's evolved over many years to keep up with growth. And we're going to cover some areas like our feature set and capabilities that we've added. We're also going to talk about how we have evolved our architecture to be able to deliver that for you, and even some team culture aspects as well. And we have product and engineering on stage for a reason. Maybe we're going to do a live demonstration of how we hash things out in practice and decide between investing in innovation and feature roadmap or operations.
So I bet most of you are vaguely familiar with EBS, but I figured I'd just give us a really brief refresher as to what EBS is. EBS is a service that provides the persistent storage, basically block storage, for EC2 infrastructures. And we refer to this storage as EBS volumes, and it's network connected, meaning that it's basically disaggregated from the actual instance itself. Now, in addition to that, it offers a whole bunch of data services like snapshots and data services and data resilience. But it's really important as we go through this talk to realize that EBS is not just a disk somewhere with your name on it, right? It's actually an entire distributed system behind the scenes that's basically continuously monitored and operated by our engineers. This ensures that we meet all of our availability and our durability and our performance goals, and it gives us the ability to move quickly and keep innovating, oftentimes without you even noticing that we're making any changes underneath the covers. We'll walk into some of those changes that we've made as we go through today's presentation.
OK, so here we have a couple of graphs just to show you some of the scale and the growth that we've had in EBS over the past few years. We have, on one side, daily IOs that we're processing every day, and we're now processing about 100 trillion IOs every single day. And we also move quite a bit of data, about 13 exabytes of data to support your workloads every single day. Now, operating at this scale can create some very interesting challenges for a product manager. One of the hardest things is that there is no such thing as an edge case when you're dealing with this kind of scale. No matter how unlikely an event is from happening, you can bet that it will happen at this scale. And when you're moving exabytes of data and dealing with trillions of I/O, even a small percentage of that still can be a very large number.
You know, the scale is great for the business, and as an engineer, it is a great technological thing to kind of focus on. But it's also a really harsh taskmaster. If you don't constantly scale your underlying systems at this rate, and you constantly revisit your architectures ahead of actually hitting bottlenecks, you're really going to run into a space that is really painful really quickly. You know, you see 100 trillion IOs and 13 exabytes of data, but if you're like me, sometimes contextualizing it really helps. So, you know, to put 100 trillion IOs a day into context, the average person is said to speak between 7,000 and 12,000, maybe 15,000 words a day. So let's call that 12,000 words a day. There's about 8 billion people in the world. So if we do the quick math and we take a look at it, EBS is processing daily about the same number of transactions as all of humankind is speaking words in an average day, right? It's a really big number. Similarly, who here remembers AOL CDs? I know I'm dating myself. Come on, I know it's more than those, right? Remember, it used to feel like you got an AOL CD every month, right? Well, 13 exabytes is the equivalent, staying with my humanity analogies, of delivering an AOL CD to every inhabitant of the earth every 10 hours, 365 days a year. That's 2.5 CDs a day. So it's a lot of data transfer. And if you're not careful at this scale, you'll find yourself spending an exorbitant amount of time catching up on operations or dealing with tech debt, even though we really abhor the term tech debt at AWS, instead of actually innovating for your customers.
Yeah, that's right. So what we're going to try to do today is talk about how we handle this level of growth. Both how do we think about innovation that fuels this growth, but also from an operational perspective, how do we keep growing and supporting growing at this kind of pace? So our formula consists of mainly two things. The first one is customer obsession. You probably have heard that about Amazon before. But we really do believe that focusing on our customers is really what drives innovation. And we really want to figure out how we can help you do more with less over time. But we also need to know that if we're going to be meeting your customer needs and driving innovation through that, we have to be world-class operators. And being world-class operators at that kind of scale, what that looks like in practice, that's some of the things that John is going to talk about as we go over the evolution of EBS. So how do we evolve the service? How can we help you do more with less? This has been our guiding principle since we started AWS, really. And that's how EBS came to be. Before EBS, when we launched EC2 instances in 2006, we could say that was the beginning of the cloud. There were lots of internal debate in our team if we could launch EC2 instances just with the local store on the instance, or if we had to wait until we had persistent storage to go with that too. And we decided to move quickly with EC2 because we thought customers could really benefit from that. And indeed, they were super excited. You were super excited to adopt EC2 early on. But it was kind of a little bit feature poor. And if you moved a workload to EC2 in 2006, you really only had the local storage on the instance as your option for storage. And that local storage was ephemeral. And that means the fate of your storage was tied to the fate of your instance. So if you wanted to keep the storage around, you had to keep that instance running, even if you were not doing any compute. This also meant that if there was any issues with hardware or infrastructure that caused instance problems, your storage would go away.
You know what wasn't very tolerant of storage just going away like that? Databases. And we really quickly got feedback from our customers that, soon after launch, that they really wanted us to be able to run databases more compellingly on the cloud. And this was really two things. One is they were really looking for that disaggregation model, because when the hardware failed, they wanted to be able to start their database on a new instance. And if they wanted to scale their drives or they wanted to scale their storage, they wanted to be able to do, or those are the same things, scale their drives or scale their instance. They really wanted to be able to do those two things independently. So this is what really started us going down the path of EBS.
And that's when EBS came into the picture. When we started EBS, it was really just a way for you to have storage attached to your instance that would survive independently from that instance. And this wasn't just more reliable, but it also allowed you to save costs, because when you were not using your compute, you could terminate your instance and your data would stay there. It also made it easier to grow your databases in AWS, because now you could also scale your storage separately from your compute. And now that we have persistent storage, we also wanted customers to be able to back up their data easily. Maybe you don't need the volume around when you're not using that volume. And so we launched with EBS snapshots, the ability to take a snapshot of your volume and store that in S3.
Well, it was early days for the cloud. It was early days for EBS. And there were some limitations. If we were to clip through some of the things that defined EBS at the time, we could support any location worldwide that you wanted, as long as it was in Virginia. There just weren't any other options. If we think about blast radius, and that's going to be a big theme of our conversation today, in 2008, microservices were not even a thing, right? And you can imagine we solved the problem of the day much like the problem of the technology of the day. We had a database that stored all the persistent state associated with the configuration and all of the setup of an EBS volume. We had a data layer, but that control plane application, it was a big database powered in the front with a Java application and a set of APIs to the front. It was really one big storage manager application for the whole region. In fact, considering we were only in one region, for all of EBS. Now, if that was a difference from today, we were kind of ahead of the game in terms of disaster recovery. As Cami already just talked through, you could already create snapshots, you could store them in S3. It was a different implementation, storing them in S3, so you had diversity of implementation for those backups. But performance, maybe not so much. EBS started, of course, with a hard disk drive type. And underneath the covers, it was all hard disk drives. It was the technology of the day. And by the way, as a tech geek, hard drives are like super cool, right? Like, I don't know, you've figured out right now that I like analogies. But if everybody knows that a hard disk drive is a head floating over a platter, reading the actual magnetic state that is stored on the platter, well, if we scale the head of that hard drive up to the size of an airliner, right? This is the equivalent of an airliner flying over a field a centimeter above the ground at 400 times the speed of sound, reading things the size of blades of grass over something the size of Ireland. It's really cool, but it's also really physical. And being really physical, it has its limitations, particularly for small I/Os and random I/Os. And so in early EBS, it was really common to see all kinds of outlier latencies. And outlier latencies of 100 milliseconds were really common. And from a configuration standpoint, of course, it was really only one EBS volume type. We called it standard at the time. And I think we had like 2 instances at the time, a C1 and an M1, only in your common T-shirt sizes. I think small, medium, large, and extra large. There were no 48 XLs in this time frame.
OK, so you could boot your instance but from a large object, but you had to create and manage that separate from an EBS snapshot. And this was a lot of what we in AWS called undifferentiated heavy lifting. And we thought we could do better for our customers. And so we created the concept of an EBS-backed Amazon machine image. And these AMIs were based on snapshots, and they allowed you to boot your EC2 instance from an EBS volume. And we take this for granted today, but EBS-backed boot allows you to stop your instance and restart it later. And it also allows EC2 auto recovery to automatically move and restart your instance when the underlying hardware has an unexpected failure. So this is a pretty important capability for resiliency.
I had briefly talked about Storage Manager. And we're really innovative with our names. You'll find that we name things really well in EBS. Storage Manager was that one big monolithic application that stored all of the data around the configuration of an EBS volume. And we learned early on that we were going to build data stores, right? Servers that actually had the durable storage to store the actual bytes of your disk, right? And we put those in availability zones. But that storage manager, he was involved in everything that happened in that region. The volumes, as I said, were stored on these storage nodes, and the storage nodes managed hydration from S3, and they managed actually the replication and the presentation to EC2. But when we first built EBS, that storage manager did all the attaching and the detaching, all the creation and the deletion. It was involved in the recovery and the workflows, the performance monitoring, and everything. And as we scaled our infrastructure, it became very clear very quickly that, hey, you know what? This fault tolerance domain of an availability zone for the actual data was super interesting and super useful. But that storage manager was going to cause us problems because actually having a volume dependent on a regional service for its actual repair functions turned out to be a real hard problem. And over time, our thinking really coalesced into this. And this is a really common pattern that you'll see in lots of AWS services, where we talk about a control plane and we talk about a data plane. For EBS, the data plane is that persistent storage layer. It's the EBS servers, it's the network, it's the EC2 infrastructure that connects to it. And the control plane is all of the mutating options on that EBS volume: creation, deletion, attach, all of the various things that you can do to a particular volume. And Storage Manager was our control plane in this time frame, doing all of those various workflows in addition to things like replication management, like the replica placement pieces. And so, we looked at this, and we were scaling, and we just realized, and this is a very common theme, that we had to prepare for where we needed to be in the future rather than where we were today. And we really said we need to start to split out that functionality and make the data plane independently available. And that realization really led us to thinking about, hey, how do we take that storage manager and how do we build a service? We called it the configuration manager. Remember I said we were really good at naming? How do we bring that configuration manager, the part of the control plane that was necessary to manage the data plane, and bring it out into a separate service? And so we built CM. The configuration manager really allowed us to pull all of that information out of the storage control plane, and it was responsible in the data plane for managing, for instance, all of that replica management, who is the correct writer on this volume, that relationship between an instance, the pieces of the EBS infrastructure, and the storage infrastructure. Now, that configuration manager was actually a Paxos-based replication infrastructure, but most importantly, it was zonal, right? This is the first time in EBS's history that we had a zonal data plane, something that you kind of take for granted today because EBS is a very strongly AZI service, availability zone independent. Now, this CM service, this configuration manager service, really allowed us to create a data plane that was zonal, and yet we still had this control plane that was regional. And so, again, you go back to basics, and while we were happy with the improved scaling and the blast radius that the configuration manager offered us, we really started looking at storage manager, right? That storage manager functionality that was taking care of creates and deletes and snap, attach, and detach. And we started to componentize it. And another really key thing is every single time you hear me talk about componentizing a service, we're mitosising the team at the same time, right? Each one of these components has a team that is dedicated to it, is looking at the customer-facing metrics for that component and creating a refreshing cycle, a recursive cycle of looking at how their customers are experiencing the service, how they're improving the service, and what their roadmap is on that service. So we took Storage Manager and we pulled out snapshots and we pulled out attachments and we pulled out account property services and a few other things. And then you're seeing where this is going. We said, man, we continue to grow. Remember that almost exponential growth that we were talking about. And we realized that our data centers at this stage, right, our availability zones were comprised of tens, if not many tens of individual data centers. Did we really want a blast radius for EBS that in certain failure conditions could take down a whole AZ? And so we really started to look at the problem, again, with fresh eyes from the other end of the telescope and try to figure out, well, what's the smallest unit that we can create in terms of data zone availability? And this is where we came up with cells. So we took that configuration manager, which was one database for the data plane in each one of our AZs, and we invented what we call Physalia. In fact, if you take a look at the QR code, you'll see a paper that we published on Physalia. But Physalia basically takes the core pieces of data plane metadata between instance, server, and the parts of the EBS infrastructure that are using that particular volume, and it enumerates that in a cell. And it stores millions of these cells in millions of individual Paxos clusters in EBS. And so now the blast radius for our data plane is not zonal, it is cellular. And that's a approach that you'll see used over and over and over in AWS.
Okay, so while we were busy making these big architectural changes to keep up with EBS growth and geographic expansion of the AWS infrastructure, our customers, you, were busy building applications that demanded more and more performance from EBS. You might remember earlier, John talked about hard disk drives.
Super cool.
And EBS was originally based on HDDs. And they're great for storage, but they're not so great for small random IOs. And it turns out that small random IOs became more and more common as you moved more of your databases to AWS. And so back then, this was about maybe around 2012. So EBS had been around for maybe 4 years. And we still offered best effort performance, right? And that performance averaged about 100 IOPS. No consistency. And the lack of consistency started to become a real struggle. Predictable performance was probably the single topic of all our customer conversations back then. And so in 2012, we launched IO1, the first EBS volume type that offered provisioned IOPS. And so now you could actually provision performance on your volume based on the requirements of your workload. And that gave you a more predictable, consistent experience with performance. However, it was not possible to deliver this experience with an architecture based on HDDs. And so this was also our first volume type that was based on SSDs. And so, as I said, EBS had been around for 4 years. We had a pretty large customer base already back then, and we had a fleet with thousands and thousands of servers in dozens and dozens of locations. And we had to go and, to be able to deliver this experience, replace the fleet with SSDs in all of these locations.
Yep. And remember at the beginning of the presentation, I said, hey, EBS is just not a bag of bits with your name on it somewhere on a disk. It's really a very live, distributed system operated and curated by the engineering team. And this was very much akin to basically changing the engine on a flying aircraft for EBS. Because, by the way, all those servers were full. They had all of our customers' data on them. And yet we figured out how to actually go through all of our data centers worldwide, add disks to them, and then create a SSD-based offering with all of the changes necessary in our system stack around logging and around leveraging the new SSD devices, all while keeping our customers' operations ongoing, all behind the scenes. If you want to hear more cool war stories about how we did this, I would really encourage you to check out Andy Warfield's talk on Wednesday, where he's doing a storage innovation talk. And he'll talk about some of the crazy things that we ended up doing during this time as we retrofitted our fleet worldwide with SSDs.
So around this time, we also launched the first EBS-optimized EC2 instances. They had a dedicated network throughput for EBS volumes. And that really allowed you to maximize performance, and fully utilize the IOPS that you provisioned on your volume. Now, originally, this was an opt-in feature, but just about every customer started choosing this. And so eventually, we made it the default on most EC2 instances since 2015. So this chart is showing a little bit of the evolution of performance on EBS volumes just between 2008, since our launch in 2015, when we made these announcements, IO1, provision performance, and EC2, EBS optimized instances. And you can see really upgrading our fleet with SSDs and having dedicated bandwidth for EBS on the EC2 instance they were two investments that really paid off because it allows us to move much more quickly with performance improvements. You can see that from 2012, when we started to make these changes, our performance per volume really took off. Within a few years, we launched not just volume with provision performance, but we also increased IOPS and throughput by 20x.
You know, it was about this time that we also started to be able to leverage lots of the investments that we, AWS, were making in our overall ecosystem and really leverage some of the technologies that we were using in other spaces but had direct applicability to EBS. And certainly one of those was the Nitro card for EBS. All of the instances that you consume now are Nitro-based, and you know that for its security posture, you know it for the fact that it be able to give you all of the performance of the infrastructure that you're running on. But for EBS, it also allowed us to present basically native NVMe controllers, right? Basically native NVMe devices to an instance. And it also allowed us to optimize the path from that instance back to the EBS infrastructure and provide lots of other functionality like full offload for our encryption infrastructure and those kinds of things, meaning that there was no performance difference between encryption and non-encryption on a Nitro-based infrastructure. This really became our kind of center point for how we drove faster and faster evolution on the client side, and you'll see later that we end up leveraging this Nitro hardware for even more as time goes forward.
All right, I'm going to skip ahead a few years. That was 2015 EBS optimized instances, IO1 volume. So I'm going to skip ahead a little bit to talk about one of your favorite launches, GP3 volumes. And when we first launched a general purpose volume, that was actually after we launched IO1. It was really just a way to give customers an easy out-of-the-box experience. Many of you told us, I just want a volume that just works. I just want to configure the storage capacity and just give me performance that works for the vast majority of workloads. And that was GP2, our first generation general purpose volume. You would just tell us how much storage you needed, and we would give you 3 IOPS per gigabyte provisioned, and that worked really well for many, many workloads. It was hugely successful. And soon after that, and you may sense a theme here, we launched that, and then you started telling us, you know what, I actually have workloads that need a little more performance than that. But with GP2, you're making me add storage that I don't need to get to the level of IOPS that I want. And so then we launched GP3. And with that, we allowed you to scale your performance and IOPS without adding more storage to it. And around that time, we also launched IO2 volumes. This was our first 5 nines durable volume. This is a really big change in EBS as well. IO2 is our second generation provisioned IOPS volume. And 5 nines durability is a long way from when we first started EBS. When we first launched, our goal was to have the same durability that you would get from a common disk that you would have in your own data centers. And in reality, volume was striped across multiple disks, and we had to replicate it. But effectively, we wanted to give you that durability that you were used to. And again, we launched that, and then EBS volumes would fail sometimes, and you told us, I need more durability than that. And with IO1, we launched with 3 nines durability, and that was a 20x improvement over the typical commodity disk. But we evolved IO1 to add more and more performance to it. That enabled you to move some of your most critical workloads to AWS. And you told us that you needed even higher durability than that. And so for these most critical workloads running on EBS, we now have a volume with 5 nines durability. And that's 2,000 times more reliable than commodity disk drives. This was a really big decision for us, launching a 5 nines durable volume. It required us to go back and rethink failures in EBS.
You're noticing a theme. Go back and reevaluate architectures and failure points. And of course, failure points are not just limited to the control path. We talked a lot about the control path so far because it was the first thing that we kind of tackled. But on the data plane, we had to use many of those same approaches to go build the infrastructure necessary for IO2. Lots of the volumes are split into many different shards, and those shards are no longer constrained by individual nodes. We'll also talk a little bit about how we do rebuilds and accelerate the actual recovery from the inevitable failure, as hardware always does fail. But we also did a whole bunch of software improvements to improve our replication and make the time between resolving, getting back to a durable state in our system faster and faster to be able to hit our models for a IO2 durable model. Now, as we broke the volume into many different pieces and stored it across our storage infrastructure, I figured I'd give a little bit of a view in terms of how to think about this in the EBS infrastructure. Here we have, a set of servers and a set of volumes, roughly denoted by the color of the volume. And, if you had a failure, and in the storage world, this could be a hardware failure, this could be a planned or unplanned maintenance outage, right? Like, we don't really make a big difference in our automated systems between something that gets taken off administratively versus something that fails because there was a hardware failure. It makes it easier for our engineers to reason over what the corrective actions ought to be. But that server is removed from service. After it's removed from service, we figure out what pieces of that volume are basically under-durable, right? And then we build those pieces in other servers with the pieces that are remaining. Now, what does this mean in practice? In practice, it means our rebuilds are very parallel in EBS. It is very common in large AZs to find hundreds or thousands of servers participating to repair the blast radius lost of one server in that infrastructure. And of course, completing it in a very fast time frame, which, by the way, if you work out the math models, means that we can provide a higher level of durability guarantee for that infrastructure.
Okay, back to the product roadmap. In 2021, now we had a 5 nines durable volume. You started moving more of your critical workloads to EBS. And it turns out these critical workloads tend to need a lot of performance, and they are particularly sensitive to latency. And so in 2021, we launched IO2 block express volumes. So with their 5 nines volume, but with a single one of these volumes, you can reach 256,000 IOPS at sub-millisecond latency. And the truth is, again, another theme, you never stopped pushing us for performance, to deliver more performance for your workloads. And so we never really stopped working on performance. It's something we're constantly, continuously doing. And today, with EBS, you can achieve up to 400,000 IOPS and 100 gigabits of throughput per EC2 instance. And so this is expanding that chart from earlier. We can now see from launch to 2023 the evolution of throughput and IOPS for EBS from a volume perspective, that's the pink bars, and from an EC2 instance perspective, that's the blue bars. And we've really come a long way. And John walked us through some of the infrastructure changes that happened in EBS to be able to support this level of performance. But these also happened alongside many other interesting changes and improvements that we've made across AWS that we were able to take advantage of in EBS to remove performance bottlenecks. And so the Nitro system was one of them. We talked about that earlier. But the SRD protocol was another interesting one.
SRDs are a super important one. Of course, EBS, when it was first built, used TCP. And TCP, man, we know it, we love it. It's got some great strengths. One of its strengths is not path management in the face of failure. As you probably know, TCP is session-based, and if you have a flapping link, or if you need to reconnect the session, you basically have to go through what is a pretty long and arduous task to basically get another route to an endpoint and set up a new session in the midst of networking failure. SRD. I talked a little bit about Nitro and how Nitro was an enabling technology, but SRD came on the heels of Nitro. And Nitro was a recognition that our problem in EBS was very similar to what other teams in AWS were facing. And so AWS's response was very much, let's rethink our core architectural assumptions. And how do we really embrace the architecture of the network that we use to power all of our data centers. And that's where SRD really was birthed. SRD is scalable, reliable datagrams. But if you take away one thing from SRD, it's path aware. What it does is it allows the protocol itself to understand all of the routes through the network. It has very fine-grained timers that are at the microsecond level, keeping the health of all of these paths alive. It will resend packets during different paths if a path is deemed to not be accessible, meaning that it actually leverages the fact that our networks have a tremendous number of paths through them from an EC2 instance to an EBS server. And so SRD helped us in several big ways. One is it helped us really eliminate a lot of the tail latencies associated with TCP, which was a huge improvement for our customer experience. Another way is that because it was leveraging multiple paths, it also allowed us to improve the bandwidth delivery of the exact same physical infrastructure because it was allowing us to leverage multiple different ways of delivering that data through the network. As a result, the customer impacts have been relatively large, right? We have about 90% lower tail latency with IO2 riding over top of SRD as opposed to IO2 not riding on top of SRD. And this is all because of that resiliency in the networking layer and the fact that the system can recover from the rare failures that at our scale happen all the time in a network.
All right, so let's talk about tail latencies a bit more because this is super, super important for you. You have told us over and over again that for your most critical applications, the ones that are driving a lot of I/O, variability in performance can be a struggle. And so that's why our team spends so much time thinking about latency, monitoring latency, trying to identify in those far, far outliers what's driving latency and then driving that down. And so in this chart, we are showing IO1 latency. When we first launched IO1, as I said, it was our first provisioned IOPS volume, and we offer consistent performance. And we knew that consistency was important, and so we designed IO1 to deliver single-digit millisecond latencies and to deliver within 10% of that performance 99.9% of the time. So you can see in this chart, in the percentiles, we're actually delivering single-digit millisecond latencies past the 99.9th percentile. But as you go farther out into the nines, you start to see more variability. And we thought we could do better for you to support those critical workloads that you were moving to EBS. And so that's what IO2 Block Express comes to solve. You can see that orange line right there. That's IO2 Block Express latency. And we designed it, as I said, to support sub-millisecond latencies, but we really focused on the outlier control experience with this. SRD really helped, and we wanted you to have the highest level of performance consistency. So improvements like adopting SRD and the Nitro card, combining that with a major re-architecture of the EBS storage servers, we were able to deliver this with very little variability in performance, even in the far outliers. So these are some of the improvements that you can see today. You absolutely loved this experience, and last week we announced that IO2 Block Express volumes are now available with all the EC2 Nitro instances, every single one of them, all of them that we launched since 2017. So it's pretty widely available now. And in fact, if you have an IO2 volume, you can change the IOPS or volume size on that volume, and you will automatically get this experience. And if you create a new IO2 volume with a Nitro instance, it will automatically run on this improved architecture and benefit from this. So you get 4 times more IOPS throughput and storage capacity compared to IO1. And you get 100 times the durability, much, much lower latency outliers. And if your application drives a lot of I/O, you can actually get up to 50% lower costs with IO2 Block Express because we have tiered IOPS pricing.
Switching gears, I figured we would get now into the second part of our session. And I figured we would cover some of the cultural aspects of our team and best practices for operating a large-scale service like EBS and, ultimately allowing us to innovate at rate. So the question that we always pose ourselves is, how do we keep growing? It's not enough just to innovate. We have to do an outstanding job operating the service. I can't stress that enough, because trust is hard-earned and it's super easily lost. We have to remain as reliable as we possibly can as we grow, so customers have the confidence to move their most important workloads onto AWS.
And we started this session talking about customer obsession and how that's really what drives this growth for us. But the reality is we've only been able to keep up with what you, our customers, needed from EBS because we were able to deliver very quickly and innovate at a fast pace. If we don't have that agility in our engineering teams, we just can't keep up, right? And so we have to do an excellent job operating the service to create that space and to create that agility. So these are two things that may seem at odds sometimes, investing in innovation or investing in operations. But in reality, in our experience, they kind of go hand in hand, and one creates space for the other.
And that brings us to one takeaway. One of our most critical mechanisms in AWS and in EBS to operate at this scale is measuring absolutely everything. I talked about how we build our systems. And as we build our systems and we mitosis a system into, let's say, two systems, we create what we call a two-pizza team that is aligned to that new system with metrics and outcomes that are directly tied to the end user. Right? What is the customer experience of your system? And those teams independently track those dashboards in these metrics. We look at hundreds of metrics, but that's not just AWS engineers peering at metrics that maybe they know, maybe they don't know. These are AWS engineers peering at metrics that define their customer experience for their system, because they're aligned to that system. And with that level of ownership, looking at all of the data and setting up alarms on that data, we hope to find these service issues well before they ever actually impact a customer. But to be really honest, at our scale, every problem is a super hard problem. And I figured I'd share a little bit about how we go about mechanizing to solve hard problems. You may or may not be familiar with Deming. Deming was a process quality engineer who was really influential for the Japanese car auto manufacturer in post-war reconstruction. And his whole idea was, you build a plan, you do the plan, you check the outcomes of the plan, you act on the outcomes of that. And it's a very well-established processing approach. We do not follow Deming to the T, but this is very close to the actual scientific process as well. And we follow that to a T inside of EBS. We very much study the data that we have from that measurement of everything that we talked about. After we study the data, we figure out what do we need to hit that goal in terms of defining deliverables. And then we create owners and actions for those deliverables and aggressive timelines. We go and we deliver those, and we do the cycle over and over and over again. Now, this might sound like a platitude, but we're actually built this way underneath the covers. There's a cohort, for instance, in my team that is focused on performance outlier reduction. That cohort, as a team focused on performance outlier reduction, goes through this cycle, owning their roadmap, owning their deliverables, reporting out to the whole EBS leadership team, as we make sure that we are driving a deep state of continual innovation on, for instance, that goal. And as an example, for reducing outlier latency, if I were to scroll the clock back 2 years, if you were put yourself as a fly on the wall in that cohort, they'd say, well, I don't even know what the outlier latency is. We do 100 trillion IOs a day. How do I know whether or not a pin drops in Japan or a pin drops in IAD? Well, one of the first things that they delivered was, I track and know the performance of all 100 trillion IOs a day in EBS. So going back to our contextual comparison, now we have a system that is creating as many words, or as many IOs as words spoken by humankind every day, and a configurable system for our engineers to figure out if any one of those words was mispronounced, right? So that was the first deliverable. Now they can see the problem. After they can see the problem, the question is, well, it happened. How do we know what all of the causal events around it was? So you build a tracing infrastructure that's configurable by the engineers to leave breadcrumbs for any I/O longer than X amount of time. But that doesn't matter. That's all sausage building, right? That is how we go and mechanize it. What are the outcomes from a customer perspective? Well, this is actual 100 millisecond compliance for IO2. This is measured worldwide. This is over the last 11 months. If you stare deeply at the compliance, this is the percentage, with the top being 100, of our IOs completed worldwide below 100 milliseconds. If you stare deeply at the chart, I bet you'll be able to see some deployment timelines as we continually, out of the impact of this cohort, push new software, push new improvements, improving our customers' experience underneath the covers. But it doesn't always go well. Sometimes we have errors. And I think in any large system, you're bound to have certain defects escape. And one of the things that we do at AWS is very much focus on being reflective around the escapes that we have and when we do find an error. It's about diving in after remediating the issue, understanding the impact so that we can communicate clearly with our customer base during the impact, but then post facto, really diving into all of the whys about why it happened and driving those corrective actions.
And we'll reprioritize work to be able to put those corrective actions into the systems and ensure that things continue to run smoothly as we scale. Because again, one thing you'll learn as you scale is there is no edge case, and no matter how unlikely an event is from happening again, it will definitely happen again if you don't fix the root problem.
Yep. And so I figured I'd go through an example. In 2001, we started an optimization to improve the communication in EBS between the data plane and that Phasalia cell service, eliminating an API hop through a different service. It was really awesome. It improved the tail latencies of certain events. It deployed really well. It didn't trip any of our alarms. Of course, we had all of our automated deployment alarms in place and everything else. But it didn't go quite as planned. And in AZ, it was a zonal issue because EBS, remember, EBS data plane zonal. But EBS in a single zone in IAD, or in US East 1, after experiencing another event, I can't remember whether or not it was a power failure or whether or not it was a network partition, but it caused the EBS servers to query that Phasalia metadata service for configuration information, but it was bimodal in behavior. In other words, normally the transaction rate to this component happens based on call flow, but in this power failure or network partition event, it all came at once. And the new interface that we had created was slightly less optimized than the older interface, resulting in that component basically browning out. Now, this showed up as instance launch failures and the inability to create new volumes for some customers in that AZ. Of course, we immediately understood the problem. We immediately communicated to our customers about it. But we really looked deeply at, how could we have avoided this impact overall? And the answer wasn't go make that API faster. That was the first why. And it wasn't go scale that service. Maybe that was the second why. It was, you've created a distributed system sin. You have a big fleet calling a small fleet in a bimodal response, right? In other words, some failure condition results in the system operating in a way that it didn't operate before, which generates more traffic, and it's a very large fleet, the EBS server fleet, calling a proportionately smaller fleet. We got all the way down to bedrock on the whys, and we changed the architecture. It took us a long time. It took us the better part of about 9 months to go build the architectural changes in the infrastructure to avoid the big fleet calling a small fleet. But we did it below the waterline, underneath the service veil, and we did it without impacting our customers, leaving us in a spot where this class of problem can no longer even occur in our infrastructure.
This is also a great example of how operational excellence will fuel also our product roadmap. Because after an event like this, which John just talked about, it's not just the engineering teams that will go and take corrective actions. The product team will also try to find areas where we can improve the experience for customers. And so we took the same approach that John talked about earlier of creating a mechanism around this. And so together with the EC2 team, because this failure also impacted instances, we went and talked to customers who were impacted by this event. And we realized that there was a lot more that we could do to help you quickly root cause a problem and then quickly recover your application when this kind of failure happens. And so we went and created a cohort between EC2 and EBS. And this group meets every month. We defined a roadmap around that with resiliency features and assigned owners. And over the course of the last several months, we've delivered a number of features to help improve this experience. So this is just a sample of them. We launched the ability to pause I/O on an EBS volume using the fault injection simulator. And with that, you can kind of see how your application will respond and your upstream dependencies will respond if an EBS volume can process I/O. We also improved the instance lifecycle. And so now you can reliably stop and start your instance and recover your application when the EBS volume attached to it is not responding. And we also launched a couple metrics on volume health. You can get an EC2 instance view of your volume's health that will tell you if the problem is with your volume or with your instance. Or you can look at the EBS volume level metric to identify which specific volume may have a problem. Okay, so as we wrap things up, let's talk about how do we continue to innovate at scale, right? If your experience is anything like ours, you might find that investing in these systemic things will actually allow you space to innovate more on behalf of your customers.
Yeah, in terms of operational excellence, if you remember nothing else from today, I'll leave you just with a couple of things, maybe 2 specific things. One, rely on the flywheel of inspection. Inspection and ownership. That is actually the core of what the cohort that I talked about that iterates through study, build a plan, evaluate the outcomes, build a new plan, etc. is. You saw it in every example that I talked to, this inspection of an ownership flywheel. It's what we do. It's how we organize. It's how we run our roadmap. It's how we build our teams. The second thing is I would really challenge you to rethink your architectural risks as you scale. I gave you lots of examples where I said, well, we did it this way, and then we did it this way, and then we did it this way, and then we did it this way. All because we were maturing the team, the technology, and our thinking as a team about how we continue to press ourselves and raise the bar around managing architectural risks as we scale.
Okay, and I will leave you with this. I encourage you to challenge this mindset that you have to choose between operational excellence and investing in your operations or innovating in your roadmap. These things, they don't have to be at odds, right? And in our experience, they go hand in hand. And if you find the space to invest in both operational excellence and innovation in your roadmap, you'll actually find a virtual cycle where you're creating agility for your builders and you're inventing for your customers, and ultimately you're growing your business, which is what everyone wants to. So thank you so much for joining us today. We hope you've learned something interesting and that you have a great week at re:Invent.
Hey, thank you so much.